Didn't
Yeah,
get,
I didn't get that message again.
okay. Well, let's proceed, I guess.
I think it'll
Well, we'll
be
see
okay,
what happens.
Stefan. We've gotten several
Okay.
meetings in the cloud now. Bill had one today. It's in there, so I think it'll be okay.
Okay.
Yeah.
Alrighty. Well, in that case, let me begin. Everybody here, everybody comfortable? Looks like it perhaps will not be a super big group, so we can then, because of that, we can have more of a discussion, one-on-one discussion towards the end. But during the presentation, I would ask that you all put your questions, if you have any, into the chat, and I will act as moderator and then forward those questions to Dr. Murray at the opportune moments. My name is Stefan Sommer. Some of you know me. I am a board member of the Northern Arizona Climate Change Alliance and a recently retired professor from NAU. And I'm have the honor to introduce Dr. Greg Murray today. Greg is an ecologist with broad interests in tropical forest ecology, conservation biology, marine biology, and ornithology. He retired from teaching in 2021 as the T. Elliott Weyher Professor of Plant Science at Hope College in Holland, Michigan. After 35 years on faculty there, he has been involved in sustainability and energy issues in Michigan and now Arizona since the year 2000. Although he is retired from the teaching faculty at Hope, he is still conducting long-term forest research in Costa Rica. His field site at Monteverde is one of the first locations where the biological results of climate change were documented, with the declines and extinctions of several amphibians, including the golden toad. Dr. Murray, thank you very much for sharing with us your expertise on the Earth's climate systems and how they affect the distribution of species on Earth.
Great. Thank you for having me. It's nice to be here with everybody. I'm going to share my screen, and so let me know if you start to see what I'm intending. Okay.
Yes.
Do you see my title slide now?
Yes.
Okay, perfect. Okay, so what we're going to do is not talk about climate change per se, although that's obviously something that will come up. And what I really wanted to do is talk about the origins of our climate system here. And so obviously, if questions about climate change come up at the end, we can talk about those and I'm prepared to do that. But really, I want to talk about from first principles where our climate comes from. So the sort of brief outline of the talk is we'll talk just a little bit about biological productivity of the Earth, since that's what drives everything else. Then I want to have a really quick overview of biomes and their distribution, and then talk about the energy balance of our planet. And then dive a little bit more deeply into the origins of climate in our on our planet in terms of the Earth's shape, its position in the solar system, physical characteristics of gases, and stuff like that. And we'll spend a fair bit of time on that because I think it's not very well understood by a lot of people. And then we'll talk about common plant and animal adaptations to climate and convergent evolution, because that's really kind of where biomes come from. And so we'll talk then about some examples of major biome types and the climates associated with them. So more than anything else, it's the Earth's climate that determines the distribution and abundance of plants and animals and other living things across our planet. Obviously, soils are important and lots of other things are important, but it's really the climate that is the major driver of most of those patterns. That begs the question, what do we mean by climate? What creates it, and how does it affect the distribution of living things? Well, really, climate consists of weather patterns especially temperature and precipitation, that prevail over a long period of time, like at least decades, at a particular location on the Earth. And so lots of times people distinguish between weather and climate, and they should, but really integrated over long periods of time, weather becomes what we associate as climate for a particular part of the Earth. Well, this is a really nice graphic that I use a lot in teaching, have for many years. It's a false color image of the Earth's primary productivity. And climate is the primary driver of the pattern that's shown here. It's a false color image, but it does have a particular coding of the colors. Primary productivity is just the rate at which energy is captured from the sun via photosynthesis and incorporated into the bodies of living things. And of course, everything else depends upon it, including our own existence. So on this slide, the cooler colors on land, like green, for example, indicate higher productivity, and the warmer colors like yellow and orange, like you'll see here in North Africa, those are areas of lower productivity. And so you can see that areas that are dominated by forests, like the eastern United States and the Amazon basin and parts of Siberia and so forth, are generally areas of high productivity. The areas like North Africa and the Southwest United States, for example, are areas of lower productivity. I should also point out here that the color scheme in the oceans is actually the opposite. In the world oceans here, the areas that have the warmer colors are areas of higher productivity. So for example, you can see in the North Pacific and the North Atlantic, and around the Southern Ocean, for example, and in a narrow belt along the equator, are areas of higher productivity. But these vast areas in the major ocean basins far from land, where the colors are blue, those are areas that are lower productivity. So the major ocean basins are really essentially the same level of biological productivity as a desert on land. One of the things that I always remember reading as a kid was, in popular science magazines and stuff like that, is how we were going to farm the oceans and feed the world's hungry by farming the oceans. Well, that's not going to happen unless we remove the limiting factors that cause lower productivity here. And it just happens to be nutrients, but that's a different story from what we're talking about today. So I'm not going to really talk about ocean productivity very much. So it's climate that determines whether you're standing in a system like this, called a tropical rainforest, or on a tropical savanna, or in a temperate deciduous forest like this one in the Porcupine Mountains of Michigan's Upper Peninsula. That's for char in there. Or in a temperate grassland, like the slide shown here, or in a desert. And these are all examples of biomes, which are large-scale collections of biological communities that are made up of organisms adapted to the physical conditions over a wide geographical area. Although there are some other factors like soil type that can be important too, biomes are really determined mostly by the climate that prevails at a particular spot on the Earth's system. So we're going to talk about where climate comes from in just a minute, because the ways in which we're changing it make perfect sense in terms of well-understood principles of physics and chemistry. So biomes, like I said, are just large-scale collections of biological communities. They're not the same thing as communities, but you can think of it at an even larger scale, that are made up of organisms that are adapted to the physical conditions over a big area. And so we're talking about things like this. This is the distribution of major biome types across the Earth. And you can see that there's a strong correlation with latitude. So for example, we find in areas of the tropics, we find tropical rainforests, whether we happen to be in South America or Africa or in in the parts of Asia or Australia. If we go to other areas, we're talking, in a certain latitudinal band, we may very well be in desert. But it's not just latitude. There's a lot of diversity even at a particular latitude. So for example, even here in South America, depending on where we are in South America, right along the equator, we might be in a tropical rainforest or we might be in a tropical savanna. And so there's aspects that track really well with latitude, but that isn't the whole story. So the most important aspects of climate are temperature and water availability. And to a large extent, it's water availability itself that is dependent upon temperature. So we're going to talk mostly about those. It's not to say that wind patterns are not part of climate, and in fact, we'll talk about the origins of the prevailing winds on the planet too. But what is it that drives the patterns of temperature and water availability? Well, I want to talk about the Earth's energy balance in a little bit of detail and then dig into it a little bit farther. By the way, I'm using a bunch of slides of figures from a textbook that I used to use while I was still teaching. In the most general terms, the Earth's temperature is determined by the balance of energy radiated by the sun and absorbed by the Earth, and the energy that's radiated by the Earth back out into space. And whatever energy is absorbed by the Earth and not radiated back into space causes the Earth to be warmer than it otherwise would be. So in this figure, you can see the incoming solar radiation is just assumed to be 100 arbitrary units here, of which 32 units are reflected back out into space directly. The rest is absorbed by the oceans, the land, and the atmosphere, which heats them up. But any object warmer than absolute zero also radiates energy to its surroundings, and that's what you can see estimated over here on the right side of this figure. It's radiated by the oceans, by the land, and by the atmosphere. But some of that gets absorbed again by atmospheric gases. And so there's a variety of means by which people can measure these things. They're measured by remote sensing on satellites and so forth, and by a bunch of other kinds of instrumentation. We do have a really good idea, a very precise idea of what the Earth's energy balance is, and it's just summarized in this figure here. Well, what I want to do is say at the outset that Earth's climate is complicated in the details, but the basics are actually pretty simple and come down to just a handful of basic facts concerning the shape of the Earth, its position in the solar system, along with some basic chemistry and physics. And I want to focus on these basics, but in three groups at first, to show how they generate the basic pattern of Earth's climate. And then we'll talk about a few of the details that result result in finer scale patterns. So first of all, the Earth is round and it's exposed to parallel rays of the sun. Parallel rays from the sun because the sun is much bigger than the Earth and it's far away. And secondly, the Earth revolves around the sun. Thirdly, the Earth rotates on its axis west to east. And fourth, the Earth is tilted on its axis right now about 23.5 degrees. And so these are things that everybody knows. They're kind of within our general experience. And so a fair bit of climate derives just from these. And so we'll talk about these first and then layer on some other stuff as well. Together, the first, second, and fourth of those factors means that the sun's parallel rays strike the Earth's surface more perpendicularly near the equator. but at a greater and greater angle as you move towards the pole. So whether you're talking about the North Pole or the South Pole, photons or light rays, depending on whether you want to think of light as waves or particles, they get spread over a larger and larger surface area the farther away from the equator one goes. And so that's a less dense interception of energy per unit surface area of the Earth the farther you go away from the equator towards the poles. And now, well, let me go back to this one just a second here. And that's just sort of summarized here. By the way, it looks to me like on the date that this figure is showing, it looks like the most intense solar radiation is hitting the Earth at about 23.5 degrees north latitude. So what would this date be? Anybody want to just chime in? Maybe the summer solstice? Remember, the Earth is tilted on its axis 23.5 degrees, but it maintains that same tilt on the axis as it also revolves around the sun. So when I go to this next one here, because the Earth keeps its same 23.5 degree tilt on its rotational axis and revolves around the sun in a year, on 2 days of the year, the sun is directly over the equator at noon. It's on this date and on this date. That was just yesterday, September 22nd, okay? And we call that the autumnal equinox because the sun is directly over the equator at noon and the day and night are the same length. They're each 12 hours. That happens on another day too, 6 months later or 6 months earlier, because as the Earth is revolving around revolving around the sun, but maintaining that same tilt on its rotational axis, the part of the Earth, the latitude of the Earth that's receiving the most intense solar radiation changes. It varies between 23.5 degrees north latitude, which we call the Tropic of Cancer, and 23 degrees south, or 23.5 degrees south latitude, which we call the Tropic of Capricorn. That's why those are called the tropics. And so, like I said, the autumnal equinox was just yesterday. 3 months after the autumnal equinox, the sun is going to be directly over 23.5 degrees south latitude at noon, and that's the shortest day and longest night of the year in the northern hemisphere. It happens on the 21st of December, and we call it the winter solstice. 3 months after that, we get back here to the vernal equinox, when the day and night are the same length again, and the sun is directly over the equator again at noon. 3 months after that, on 21st of June, the first day of summer, the sun is directly over 23.5 degrees north latitude at noon, and we call that the summer solstice. It's the longest day and shortest night in the northern hemisphere. Obviously, everything is a mirror image of that in the southern hemisphere for the same reason. But wherever the sun is striking the Earth's surface most perpendicularly, that's where the energy interception by the surface of the Earth is greatest. And so because the latitude that gets the most intense solar radiation changes, the latitude where the surface and atmosphere is heated the most changes throughout the year. And that's where the seasons come from. I don't know if you ever used to watch sometimes Jay Leno's show. But Jay Leno, every year, he used to go to my alma mater, place where I have 2 degrees from because it was close to Burbank, it's Cal State Northridge. And he would go on graduation day and he would interview people and ask the graduates while they were still in their caps and gowns some things that he thought that they should know. And one of the things he asked them a few times that I saw was where the seasons come from. And I was always embarrassed because I had 2 degrees from this place, and people would say all kinds of stuff like, usually it's because of the Earth's elliptical orbit, and sometimes it's closer to the sun, sometimes it's farther away. That's true. The Earth's orbit is elliptical, but that has nothing to do with the seasons. It's the tilt on the axis that causes the seasons. Okay, so now let's consider the effects of the composition of the atmosphere. We've talked about the first four of these having an effect, and we've talked about part of the origins of climate from that. But now let's add in the fact that gases in the atmosphere absorb energy in different parts of the electromagnetic spectrum. This is a little bit more obscure, but really important, and it's one of the parts that we're changing through human activity. So some basic physics that governs the Earth's heat budget via absorption of energy from the sun and radiation back into space. Any body like the sun, the Earth, or even a human being radiate energy in a portion of the electromagnetic spectrum that depends on the body's temperature. Okay, so the surface of the sun is about 5,500 degrees Celsius. So it radiates energy over a broad range of wavelengths, but it has a peak at about 0.4 to 0.7 microns, which is what we call the visible part of the spectrum. So this, shown here is the radiation spectrum of the Earth, of the sun. And our sun is actually a greenish star. It looks more yellowish to us, but that's because of scattering by our atmosphere. But if you go out into space, it has its peak in the green part of the spectrum. Well, okay, so the Earth and whether we're talking about the land or the oceans or the atmosphere, absorb some of that energy and they heat up and then they radiate it back into space. But again, because the Earth is cooler, it radiates in a different part of the electromagnetic spectrum. So the Earth's temperature on average is about 17 degrees Celsius. And so it radiates at much longer wavelengths, roughly with a peak from about 3 microns to about 20 microns. And that's not in the visible part of the spectrum. That's actually in the red to infrared part of the electromagnetic spectrum. Now, it turns out that, that different gases in the atmosphere absorb energy at those different wavelengths differentially, okay? And so that's why we refer to them as greenhouse gases. Now, I'm going to show some of these absorbance spectra in a minute here, but you might imagine that the gases in our atmosphere are pretty much transparent to the wavelengths that the sun is mostly radiating in, right? I mean, that's why we can see the sun. That's why we call them the visible wavelengths, because our atmosphere doesn't absorb very much in that part of the electromagnetic spectrum. But that's not true of the wavelengths that are radiated by the Earth. They absorb several of the gases in our atmosphere absorb more strongly at those wavelengths, and that's why we call them greenhouse gases. So we'll talk in a little bit more detail about those. Okay, trying to get to, okay. So let me get to the next slide. Here we go. Okay. So these are just absorbance spectra for oxygen and ozone, for carbon dioxide, and for water vapor. And these are easily measured in the laboratory. You don't have to measure these from out in space. You can measure them in the laboratory with really precise instruments. And it turns out that the story is complicated, but you can see that at the wavelengths that the sun is emitting from 0.4 to 0.7 or so microns, and that's what this sort of shaded area is here, the gases in our atmosphere absorb some energy at the really, really short wavelengths, and at some longer wavelengths, but not very much here in the visible part of the spectrum either. Again, that's why we call it the visible spectrum. If our atmosphere absorbed those wavelengths, we wouldn't be able to see them very well. So our atmosphere is pretty transparent to energy at those wavelengths. It reaches the surface of the Earth, heats it up, and that in turn heats the atmosphere. But some of the gases in the atmosphere absorb a lot of energy at the wavelengths at which the Earth is re-radiating back into space, the infrared and far infrared from about 3 to 20 microns or so. And that's what this shaded area is here. Chief among those is water vapor. And obviously we're only showing some of the gases here, but the most relevant one. But water vapor it absorbs really strongly in that part of the electromagnetic spectrum, in the infrared to far infrared. And in fact, if we didn't have so much water vapor in the atmosphere, our planet would be really cold. The net effect of the greenhouse gases in our atmosphere is to warm the Earth by about 33 degrees Celsius. So without those greenhouse gases, our planet would be pretty much uninhabitable to us. But look at carbon dioxide. It has 2 absorbance peaks in that part of the electromagnetic spectrum. And so increasing the concentration in the atmosphere of carbon dioxide is going to make the atmosphere absorb more of that energy that otherwise would have been re-radiated back out into space. It traps it and therefore is expected on the basis of first principles from physics to warm the atmosphere. There's a peak here in oxygen too, and I'll show another one in just a minute because it's really concerning as well. These are not the only greenhouse gases, but they're the ones that we're changing the most. Here's another one of these, and this
Murray?
one,
Dr.
sorry,
Murray?
go ahead.
Sorry, we have a question and I didn't notice it right away.
Oh yeah, I can't see the chat.
Yeah, no,
Go ahead.
but the question is about the tilt of the Earth's axis. So sorry, I'm coming in with it a little bit late, but the question is, does that tilt change? And what's the periodicity, or how fast does it change?
It does change, but it changes over very long periods of time. The tilt the tilt of the Earth's axis changes from about 21.5 degrees to about 24.5 degrees or so. It does so over a cycle. It's called a Milankovitch cycle, and that cycle lasts for about the period is about 40,000 years, I think. And the change on that, that's one of the factors that actually leads to the ice ages and interglacials, because when the Earth is, when the tilt on the axis is greater, the seasonality is greater, and so it can put the Earth into a colder period in the northern hemisphere. But that's not involved at all in the climate change that we're experiencing right now. The period is much too long to have any effect on our current climate change, and that's been investigated quite a bit, as you might imagine. Is that okay?
Yes, thank you.
Okay, so here are some other gases here. Even though water vapor is responsible for far more of the greenhouse effect than the other gases, the other ones are gases that we're changing quite a bit. And I've actually talked about carbon dioxide, and again, this just shows essentially the same data, but it's in a different graph with those 2 absorbance peaks in that part of the spectrum from 3 to 20 or so microns. But look up here at methane. Methane is a really interesting one in that it has 2 absorbance peaks in the infrared and far infrared too. And that's another one that we're changing quite a bit. Nitrous oxide is another one that we're changing through human activity quite a bit. And I might just add here, even though we're not really talking about climate change per se, but methane is actually many times more effective at trapping heat in the Earth's atmosphere pound per pound than carbon dioxide is. About 40 times more. It depends on the altitude at which it occurs. And we're putting a lot of methane into the atmosphere too, especially now because we're depending so much on natural gas, and our methods of mining natural gas via fracking, and then of course via leaks from wells and leaks during processing and transportation and stuff, that goes into the atmosphere, and it's a major driver of climate change that people are very concerned about now, because we haven't increased the concentration as very much until recently, but now we have been. One other thing about water vapor too, and this is an interesting positive feedback. I said water vapor is by far the most potent greenhouse gas that we have. What happens when the Earth's temperature increases? Evaporation increases, right? And so we put more water into the atmosphere. More water into the atmosphere as water vapor leads to a positive feedback and creates even more warming. So this is not something that isn't fairly well understood. It's pretty simple chemistry and physics that people have understood for a long time, but played out on a very large scale with other complicating factors. But the basics of it are pretty well understood. Okay. Like I said, I don't want to talk very much about climate change per se, but here's what we know about the history of the concentrations of carbon dioxide and methane and nitrous oxide in the atmosphere. These really have increased dramatically just since the advent of the Industrial Revolution. Obviously, there are several ways in which we put more of those gases into the atmosphere, but these graphs sort of show them as well as they're measured. Okay, so so we've talked about 5 of those factors thus far. Now here's a 6th one from physics that has a profound impact on producing our climate as well, and it's simply stuff that you might remember from chemistry classes in high school or college. It's from the gas laws that everybody had to learn. Warm air is less dense and it holds more moisture than cold air, and it also obeys the gas laws that govern density and volume as a function of pressure and temperature. So let's layer that fact on top of what we already have talked about and talk about how that influences climate. And this comes, what we're going to talk about now is the origin of vertical air movement patterns. And this is going to turn out to be fairly complicated when we then extend it to the horizontal air movement patterns that really constitute the prevailing winds that transport heat and moisture around our planet. So first of all, air is heated at the surface because the air is heated by absorption of energy from the sun directly and from radiated from the land or the water. And thus it rises because it becomes less dense. It's just obeying the gas laws. Secondly, it expands as it rises, so it loses heat, it cools. Again, just the gas laws. That happens at about 10 degrees per kilometer for dry air, but it happens at about 6 degrees per kilometer for moist air, because as moist air rises and you get condensation occurring, you gain back some heat of condensation. So air heats and cools as it goes up and down in elevation at different rates, depending on whether it's saturated with water vapor or not. And then as the rising air cools, it can hold less water. So the condensation or clouds occurs, and that's where, a lot of the rain is going to come from. So let's layer those on top. Let's explore the consequences of that for a second. So in this figure, on average, so we're not going to talk about the seasonality yet. We're just going to talk about as though the Earth always had the equator facing most directly at the sun. So then on average, the Earth is going to heat most intensely at the equator. So that's where the air is going to be heated and rise most intensively. And that creates a low atmospheric pressure near the equator. And the air flows near the surface from both the north and the south are going to flow along the surface toward the equator to replace the air that's rising at the equator. As the air rises, it cools, it obeys the gas laws, and you get condensation and clouds and a lot of rain in the tropics as a result of that. As the air rises, it can't just keep going out into space, obviously. It has to stay with the Earth. And so it spreads at higher altitude, it spreads poleward, either towards the north or the south. And it comes down again at about 30 degrees north and about 30 degrees south latitude. That circulation cell is called the Hadley cell. It's named after the person who first elucidated it or such. And so the interesting thing about that is that, remember, this is moist air that's rising near the equator, but the air that's falling at about 30 degrees north and 30 degrees south latitude is actually dry because it's lost its moisture as it rose and rained out over the equator. So this is a little bit more complicated. We have here the Hadley cell, and of course these are mirror images in the northern and southern hemispheres. If you think about what is going to happen as a result of temperature at the poles are where the Earth's surface is heated the least, and so air actually ought to be falling there. And then, of course, it spreads equatorward from there, whether you're in the northern or southern hemisphere. And then it turns out that it rises again at about 60 degrees. And so this that's called a polar cell. And it turns out that because of really the size of our Earth, this middle cell that's called the Ferrel cell is actually driven primarily by coupling with these other ones. So you have air rising here, falling here, spreading in, towards the pole there, rising again here, and then falling at the pole. So it warms enough by about 60 degrees north and south latitude to start rising there too. So it forms that polar cell, and then we get the Ferrel cell by coupling with those. If you think about what happens at different latitudinal bands here, this is really profound. Remember, I said we've got dry air falling, and so it's a high pressure system that kind of prevails at about 30 degrees north and south latitude. That's where we find the Earth's primary deserts. It's because you have high pressure there and the air is dry. And so it essentially sucks the moisture out of whatever vegetation or bodies of water are there. That's not a mistake that we find the Earth's major deserts at about 30 degrees north and 30 degrees south. Now, why only 3 cells? Why not more cells, or why not just one cell? I mean, we could have air rising most intensively here in the tropics and falling most intensively here in the polar regions, and we could just connect those into one cell, but we have 3 instead. It turns out that, this is Jupiter, of course, and you see those bands in Jupiter that you've seen your whole life. If you count those up, those bands are actually the same as these circulation cells on our planet, but there's about 6 or 7 of them in each hemisphere. And the reason for that has to do with the size of Jupiter and with the Coriolis effect that we're going to talk about next. It turns out that because Jupiter is so much larger, it breaks into those circulation cells break into more cells in each hemisphere. So that's really a consequence of the planet's size. So the reason why we have 3 mostly has to do with the planet's size. Anyway, now we've explained the north-south component of air movement patterns on the basis of those factors we've been talking about. So between the equator and 30 degrees, we've got movement in the northern hemisphere, predominantly from the north to the south. Between 30 and 60, it's from the south towards the north. And from the pole, between the poles and 60, it's from the north towards the south. And it's, of course, it's a mirror image for the same reason in the southern hemisphere. Now, those patterns have profound consequences for precipitation patterns too, and we've already talked about those a little bit. And so now we want to sort of go back to our biome map and talk about that. So we've explained the basis for different temperatures at different latitudes. We've explained the seasons and even the major north-south components of the prevailing winds in terms of just a handful of pretty simple facts about the position of the Earth and its shape and the some well understood characteristics of gases. But how do those things really result in the distribution of biome types over the planet? We've talked about these a little bit before. Well, let's talk about some more of the consequences of that. This is going to turn out to be a little bit more complicated. So we're going to go back to the Earth being round, heating unevenly according to latitude, and rotating west to east, and having an atmosphere that obeys the gas laws that we learned in college or high school. With those things, we can start to explain the major east-west components of the prevailing winds at different latitudes. So now, because the Earth is rotating from west to east on its axis, the air that's moving either north or south is also traveling to a different latitude, where the speed at which the surface, and therefore the air above it, is moving is different. So for example, if I'm standing on the equator, I'm moving from the west to the east at about 1,038 miles per hour. But at 30 degrees latitude, I'm only going about 901 miles per hour. And so is the air that's being dragged along with the land at that latitude. At the pole, I'm not really moving west to east at all. I'm just standing in one place and going around and around. And for that reason, air that's moving toward the equator from either the north or the south retains some of the east-west momentum of the latitude that it's coming from, which is less than the east-west momentum at the equator. And the result is that it appears to be deflected to the right in the northern hemisphere and to the left in the southern hemisphere. That's called the Coriolis effect. Sometimes people call it a Coriolis force, but a physicist will complain and say that's not really a force. So we call it the Coriolis effect. And it's named after the French scientist who described and explained it. So even though these predominant air movement patterns on our planet start out with a north-south direction that's determined largely by different rates of heating from the sun at different latitudes, the east-west part comes from the fact that the Earth is rotating on its axis west to east, and that's the Coriolis effect. So remember too that actually that is going to vary seasonally, because remember the most intensive latitude of heating is actually changing throughout the year from between 23.5 degrees north to 23.5 degrees south latitude over the course of the year. So are you confused about the Coriolis effect? It's pretty confusing, but what I want to do is I want to simplify it a little bit for our purposes with an analogy. And so imagine 3 trains on 3 parallel tracks going in the same direction, but this one in the middle is going 100 kilometers per hour. And this one on to the top is going only 70 kilometers per hour at the same, in the same direction. And this one down here is going 70 kilometers per hour as well. And then imagine that people are shooting at one another on different trains. They could be throwing baseballs too, that's okay. But suppose that a person sitting in this car on the middle track fires a bullet directly across at this car on the track that's going only 70 kilometers per hour. Where's it going to hit? Is it going to hit behind, on one of the cars behind, or one of the cars in front? Anybody got a guess? Well, I can't see any of you right now because I can only see my presentation. Go ahead.
It's going to hit in the front car.
It's going to hit forward. Why? Because you're firing the bullet in this direction, but it's also traveling 100 kilometers per hour in this direction, whereas this train is only traveling at 70 kilometers per hour in that direction. So it's actually going to retain some of that. It's going to retain the forward momentum from the train where it's fired from, and so it's going to hit farther forward. What happens if this person at the same time throws a baseball or fires a bullet at this one? It's going to hit behind, right? Because this train is going at 100 kilometers per hour and this one is going at only 70. And it's the bullet is only going to retain the 70 kilometers per hour momentum in that direction, okay? If you think about what would happen between this faster train and this slower train on the other side, it works exactly the same, but in a mirror image. And so you can think of this middle train here as being the equator, and this being a higher latitude to the north, and this being a higher latitude to the south. And again, what happens? Deflection to the right, okay? And what's happening when we fire the bullet from here towards the faster train? It's deflection to the right, okay? Make sure you understand that. So this looks like to the right, this you might think looks to the left, but from the point of view of where it's fired from, it's deflection to the right. Down here, deflection to the left, deflection to the left, okay? And that's basically at the surface, that's really what the Coriolis effect does. And so when we think about having explained the prevailing winds in different latitudinal bands, that's why it works that way. Remember, we have the north-south component between 30 degrees and the equator, but deflection to the right in the northern hemisphere, deflection to the left in the southern hemisphere. Between 30 and 60 degrees north, we would be moving, air moving in a northerly direction, but deflection to the right, okay? And so between 90 and 60, deflection to the right, because we would be the air would be moving along the surface in a southerly direction, but it gets deflected to the right. And of course, there's just a mirror image of that in the southern hemisphere. So now we've explained the prevailing winds in different latitudinal bands with just those basic facts that I listed. And that's where we get the northeast and southeast trade winds. That's the winds that we call the trade winds. That's where they come from. And then we get the westerlies between 30 degrees and 60 degrees. And then we get the polar easterlies between 60 degrees and the poles. Okay. So we've talked about just these, simple factors as resulting in most of those simple patterns. Just from the combination of the interaction of those different factors which are really pretty easily understood. There's a lot of detail that gets layered on top of that. We haven't talked, for example, about what happens when you put a landmass into the flow of a prevailing wind, for example, or the fact that land heats at a different rate than water does for the same amount of energy that impinges on it. We can talk a little bit about those because they're important as well. Thus far, we've only been talking about the surface of the Earth as being pretty uniform in terms of what it's composed of and how it absorbs heat. Let's talk about some of these other details. So rain shadows are a great example of what happens when you put a landmass into the flow of a prevailing wind, for example. And we have a lot of examples of them right here in North America. One from a little bit northwest of here is actually a pretty good example of that many of us have experienced. And so if you think about where the prevailing winds are during at least a part of the year, in our part of North America, they're actually coming off of the, by the way, what latitude are we at here in our part of Arizona? Well, I'm in Prescott at least. Anybody know about what latitude we're at?
37 in Flagstaff.
Okay, 37, yeah, about 34 and change here in Prescott, I think, or at least a little bit farther south from here. So we're in that band between 30 and 60. And so prevailing winds in our region during at least much of the year are from the west towards the east. And if you think about what happens as air comes in off of the Pacific Ocean, which it's carrying a lot of water vapor, and as it gets blown up the side of the Sierras or any other mountains for that matter, it cools and it obeys the gas laws, and so you get condensation occurring along there on the western slope of the Sierras or the Cascades if we're farther north for that matter, and you get a lot of rain on that side. What happens when it goes down the other side? Well, it's already lost most of its moisture, and so it's much drier on that other side. So let's, we get a very different vegetation on the east, the eastern slope and the western slopes of those mountains, and that's for that reason, and that's why we call it a rain shadow. Let's look at that in a little bit more detail here. And just kind of put some numbers on it too. Remember, I said that moist air cools at 6 degrees per kilometer, but it heats, but dry air heats or cools at 10 degrees Celsius per kilometer. So if you imagine just in a schematic view here, air that's sort of being blown up one side of the Cascades of the Sierra Nevada, and it's cooling at 6 degrees per kilometer, but then you get the condensation and a lot of rain on that side. By the time it goes over the top and starts to come down, it's dry. And so now it doesn't heat at 6 degrees per kilometer, it actually heats at 10 degrees per kilometer. So that by the time you get down even to the same elevation where you started, the air is even drier, or it's drier, of course, but it's even hotter than it was when we started on the other side. And that's just as a result of these different rates of heating and cooling depending on whether water vapor is saturating the air or not. And by the way, once you get down on the eastern side of the Cascades or Sierra Nevada, where are you? What part of the world do we call that? It's the Great Basin Desert. And that's why there's a rain shadow effect there. And so it is a really important and large scale desert. Okay, so Now back to how climate affects the kinds of organisms that occur in different places, resulting in those large scale patterns that we call biomes. We're going to see that temperature and precipitation are the primary determinants of where those biomes occur, but layered on top of those primary determinants are the effects of topography and fire and soil type and other stuff. And we might just touch on a couple of those if we have time. But this is a really good way of sort of relating biomes to temperature and precipitation conditions. And I'm going to show this several times. And we've got average annual precipitation on the x-axis, and on the y-axis, we've got average annual temperature, but it's on a reverse scale so that the warmer temperatures are down here at the bottom and cooler temperatures at the top. This figure actually traces back to one of my academic grandfathers, Robert A. Whitaker. So he was the major professor of my major professor. But anyway, any place that you find this combination of annual average temperature and precipitation, you'd be in a tropical rainforest. Okay, and so we're going to talk about those, and we'll show some examples of them as well. So just remember, terrestrial biomes are characterized by the growth forms of the dominant vegetation. And what do we mean by growth forms? Growth forms are things like grasses, herbs and forbs, succulents, trees, whether they're deciduous trees or broadleaf trees. All of these are different ways of putting together a plant, and we call them growth forms. And so the factors that figure into that include things like how the photosynthetic tissues are arranged, or if there are other photosynthetic tissues in leaves, or whether it's epidermis on stems or whatever. And it includes also things where the leaves are deployed on the plant. Are they deployed near the ground, or are they held up well off the ground? What's the total amount of photosynthetic area? Are there support tissues like wood, making it a tall plant rather than a short one near the ground? The location of the apical meristem, that's the growing tip of the stem. Is it exposed, or is it protected below the ground? And how is the root system put together? All of those are things that are different ways of putting together the body of a plant, and together they define what we refer to as a growth form. And different growth forms are really favored by different kinds of climate. Well, thinking about that, you can imagine which growth forms dominate in these different biomes.
Dr. Murray?
Yeah, go ahead.
Sorry, we've got another question, and again, delayed from when you were talking, but
Sure.
is the movement of hurricanes across the Atlantic east to west caused by the tilt of the Earth's axis effect on trade winds?
I think that in a lot of cases, because those things are they're somewhat predictable, but there are these high altitude steering currents, the jet stream and so forth, and so those I won't say that those are not well understood. They're kind of beyond the scope of what we're talking about, and I don't have a really a clear understanding of exactly why those high altitude steering currents change in the way that they do. But it's largely determined by the primary air movement patterns. But there are other things going on there. There are other high altitude winds. We've been mostly talking about the surface winds. But by the way, all of those winds on the planet are driven in one way or another by an unequal distribution of heat. And there are ways that heat gets moved around the planet. Is that helpful?
Yes. Thank you.
Okay, so so you can imagine which growth forms dominate in these different biomes. I mean, if we're in a place that's like here in the Amazon basin, it's broadleaved evergreen trees that is the dominant growth form that occurs there because the climate allows it. In a really dry place like North Africa, you can't be a tree. Trees lose too much water. That's not a growth form that works under those conditions. And so, you know, we are going to find that there are similar growth forms that dominate in places that have similar climate, but they're not related to one another genetically. So there's no overlap in the species that occur in the Amazon basin versus Southeast Asian tropical rainforest. None of the species that occur there naturally in common. But if I took you in if I blindfolded you and took you in a spaceship and put you down in one or the other, you'd recognize maybe that you're in a tropical rainforest, but you wouldn't recognize which one. Well, where does that come from? So physiological tolerances of temperature and water availability are really, you know, kind of what the plants are responding to. This, for example, is a really good way to put together a plant when water is really scarce. There are no leaves there at all. You put the photosynthetic tissues in the stem, and there aren't any leaves that would lose water rapidly because of their high surface area. These turn out to be entirely unrelated plants. They're a great example of convergent evolution because, you know, this is a cactus, but cactuses only occur naturally in the New World. This is a euphorbia, the same family as poinsettias, but they're found in the Old World. I mean, they're found in the New World too, but these are completely unrelated. But a lot of people would look at this and call it a cactus because they're more familiar with these. It's just a good way of putting together a plant. And so we've had convergent evolution, convergent on a similar growth form in response to similar kinds of climate. And we find that sort of thing again and again, where we have physiological tolerances and morphological ways of putting together a plant in response to different water and water availability and temperature in different climates. And so, yeah, like I said, we call that convergent evolution. Here's another really cool example. I don't know if you've ever been to any of these places, but if you go to tropical mountaintops above tree line, you're in a type of vegetation that's called paramo. And this is Lobelia telekii, and it's in the Lobelia family. And this is in Africa, of course. And then if you go into the Andes, this is Puya, over here. It's in the pineapple family. Here's the sunflower family on the top of Mount Kilimanjaro. This is Dendrosenecio. And if you go to Haleakala volcano and look at a silver sword there, that's actually in the sunflower family as well. And so these are really convergent on the same kind of, really similar growth form in response to the same kind of climate, but these are completely unrelated plants, even on different continents. And so we find that sort of thing again and again. Here's another one that's actually a little bit closer to what you might think of. These four pictures here are broad sclerophyll shrublands, as we call them, on 4 different continents. The plant species are entirely different in these different places, but they have similar characteristics because they have evolved similar adaptations to what we call a Mediterranean climate, hot, dry summers and cool, wet winters. And that happens to be conditions under which fire turns out to be an issue as well. I've put here that one of these is in South Africa, one's in central Chile, one's in Southern California, and one's in Spain, but I'll bet you don't know which one is which. And if I took you and blindfolded you and dropped you in one of these, you would say, I'm in Chaparral, or I'm in Fynbos, or we have different names for it in different parts of the world, but it's a broad sclerophyll shrubland. The plants are completely unrelated to one another, but they have a lot of similar characteristics. Turns out this one is in South Africa, this one's central Chile, This one's Southern California, and this one is southeastern Spain. Again, convergent evolution. It happens in animals too. We're familiar with pronghorns here, and in fact, the Europeans that first came here thought that they were antelope because they were familiar with antelope from the old world. These are not related at all to one another. Antelope capra is it's in its own family, but it's convergent evolution towards similar kinds of conditions. Flying squirrels and sugar gliders, again, different continents, really similar to one another because they have similar adaptations. Here's a hornbill from the old world and a toucan from the new world. Toucans don't occur in the old world, but the ecological equivalent of it is the hornbill in the old world. And then, of course, we have nectar-feeding birds. The hummingbirds only occur in the new world, and the old world has sunbirds that don't hover when they fly, but they have very similar ecological roles that they play. And again, those are adaptations to the kinds of habitats and the kinds of resources that they have available, being convergent in different places that have similar climates. Okay, so here's a good way to represent climate. We call it a climograph, and different people draw them differently, but I'm going to show several of these. What it does is it shows temperature on this y-axis, month of the year on the x-axis, and precipitation on this y-axis, and it's scaled so that 1 degree Celsius corresponds to 2 millimeters of precipitation. And so these graphs are also going to show when temperatures are below freezing for extended periods. That's when you're going to get this blue here. And when there's a strong water deficit, when there's less precipitation, then the temperature on that line, because evapotranspiration, or the rate at which plants and just the ground loses water to the atmosphere, which is temperature dependent. And so I'm going to show several of these. And what they're going to be is there's going to be a panel like this over to the left that has that has the climograph and a map of where that biome type occurs. And the climograph is going to go with a particular location on the Earth that has that biome type. But then I'm going to show a picture that's that same biome type, but it may be from an entirely different place. And I'm also going to show this graph as well, so we can sort of pay attention to where we are. So for example, the first one I'm going to show is tropical rainforest. And so what you're going to see here is water is never limiting. There's always plenty of water around. And so under these conditions, broadleaved evergreen trees dominate because broadleaves that are held well off the ground are the most efficient way of deploying photosynthetic tissue as long as there's plenty of water and you don't have to worry too much about water loss. The picture here is from Monteverde, Costa Rica. That's actually the place where I have spent a lot of time over the last 40 some years. That's my field site. Now, if we go to a place that's a little bit lower precipitation, but also high temperature, we're going to be in tropical seasonal forest or savanna. And what I've chosen here, and this is the climograph for it over here, where we do have a significant water deficit during a part of the year. And the photograph here is actually from Guanacaste National Park. This picture was taken only about 50 miles away from that previous picture in the mountains of Costa Rica. And you can see that a lot of the trees here are leafless, not because it's cold, but because it's during the dry season. This picture was taken when it was about 100 degrees Fahrenheit outside, but the trees are deciduous in that part of Costa Rica because of the dry season. So it's a tropical deciduous forest. Now, if we move along here a little bit farther and go to a place that that actually has really severe water deficits throughout most of the year. It may be plenty warm, but but there's really low water deficits. Then we're in what we call a desert, and in particular a hot desert. And so this is Saguaro National Park, but we find deserts all over the world. Again, roughly about 30 degrees north and south latitude, although they can occur in other places as well. And now we're going to go to a place that's a temperate evergreen forest. And on this thing, we're going to be in this part of the graph. So we're going to be at a little bit lower temperature, but again, over a pretty high range of annual precipitation. That's kind of a typical climograph that you would find for temperate evergreen forests. These, forests occur where there's enough water to make the tree growth form possible, because wherever it's possible to be a tree, trees always win because they're able to hold their photosynthetic apparatus above the level that other plants can. That's why we call them trees after all. But it takes quite a bit of water to be a tree, unless you can be dormant for a portion of time when it's drier. But when it gets dry enough, it's just not possible to be a tree. Evergreen forest dominates where the temperatures are more moderate and where water is less limiting in a lot of cases. But conifers are actually a somewhat special case. They're more tolerant of fire than broadleaf trees are. And they're more tolerant of low water availability during the growing season because they have a surface to volume ratio that's lower than for broad leaves. And by the way, I'm using this term evergreen. We think of evergreens in those of us in the United States, we think of evergreens as being things like pines and spruces that have needle leaves. That's not what an evergreen is. An evergreen is a plant that isn't deciduous. Okay, it has nothing to do whether it has needle leaves. So for example, tropical forests are usually evergreen. Most tropical forests, at least tropical rainforests, those trees are not deciduous, so they're evergreen. That's just one of those things that we kind of use the term a little bit differently than ecologists do. So if we go to a place that is a little more in this part, whoops, in this part of the graph, we're in temperate deciduous forests. Mostly these are in sort of continental climates in a lot of cases. We have high water availability over most of the year. There may be a part of the year when the water is present, but it's not available because the temperatures are so low. And so a lot of the times these plants lose their leaves in response to low temperature damage and to low water availability because of the low temperatures. And so we have the great eastern deciduous forest in the United States, or in North America rather, that is a great example of temperate deciduous forest. Here's one that's a temperate grassland. We find these in a more continental climate as well, where we get really cold winters. Again, limiting water availability during a part of the year, but it's just not possible to be a tree as easily in these conditions. So we have warm, moist summers and cold, dry winters, and grasses and forbs tend to dominate, those growth forms dominate in these conditions. And fire is often an issue in these kinds of biome types too. Also large herbivores such as bison and antelope, depending on what part of the world you're in. And by the way, if you look at the distribution of these, it's no mistake that a lot of these, the area of this biome type in the world has been converted to agriculture because the soils are thick and rich and have accumulated over long periods of time. In North America, prairie biome is by far the most endangered biome that we have, not forests. So we'll go to a little bit drier here, and now we're going to be in a part of this in a temperate shrubland over here in this part of the figure. And so these include those broad sclerophyll shrublands like we call chaparral here. It's a Mediterranean climate where we have a temperature, a strong moisture stress during that summer period with low rainfall. And most of the water that is available occurs outside of the summer months. Here's the boreal forest, also called taiga, and this is a circumpolar biome type. It's predominantly in the northern hemisphere. By the way, why isn't it also in the southern hemisphere? Here, water is limiting for much of the year because of low temperatures, and the growing season is too short for broad leaves. So it's similar to coniferous forest at higher elevations too, but you can see from the map here, we find a lot of it in the northern hemisphere. In the Midwest, you get to it on the north shore of Lake Superior. Then you're in the taiga or boreal forest, but we don't find it in the southern hemisphere much. And the reason is, look at the distribution of land area in the Earth. It's not equally distributed in the northern and southern hemisphere. There's a lot more land farther north in the northern hemisphere than there is south in the southern hemisphere. And that's really important in a variety of ways. But you can see here during a large portion of the year, there's water available. I mean, there's water present, but it's not available because of the low temperature. And if we go to even farther north or even higher in elevation, we get to tundra, in this case, Arctic tundra. Very short growing season because there's a lot of water around, but it's not available because it's below freezing. And like I said, it also occurs at higher elevation. Okay. Let me just say one or two other things, and then we'll end because we're getting really low on time. There are a bunch of other factors that interact with climate to influence vegetation, including stuff like topography and ocean currents and upwelling zones and land use patterns and fire and soil type and so forth, layered on top of those general patterns that we've been talking about. Just one of them that is interesting, and this is the last thing I'll really say anything about it unless somebody asks a question about it, is the effect of elevation. We've all had the experience of driving up to the top of a mountain and passing through different vegetation zones, really different biome types in a way. And here in Arizona, we have some great examples. So for example, if you're down near Tucson, you can be in the Sonoran Desert when you're down close to Tucson with vegetation like that at the US-Mexican border. And in an hour and a half, you can drive up to the top of Mount Lemmon and find vegetation that's dominated by spruces and firs and pines like you would find at the US-Canada border. The reason, of course, is the influence of elevation on temperature and precipitation, that is, on climate, because there's those gas laws from your chemistry class again. And so as you go up in elevation, you pass through climatic zones and therefore plant communities that are similar to what you would find at different latitudes. There's a lot more that we can talk about, but I don't want to keep going any longer. We can talk about some questions. So I'm going to stop sharing here and just entertain questions, and we can go back and look at anything we want to, or go farther in a particular area direction if we want to. So thank you.
Very good. Thank you, Dr. Murray. And since there are 9 of us, I think we can open it up for everybody to unmute and go ahead and ask your questions directly. Then there won't be me as a delay between you and Dr. Murray. I guess you
Surely I said something that was completely wrong. So let me ask all of you this. How I've been including teaching about the origins of climate in my own classes just forever, because it's part of, it's part of really basic ecology. And I'm one of those people that really likes how all sorts of stuff fits together. But a lot of ecologists are not very conversant with it and wouldn't include it in their courses. How common knowledge is what we've been talking about today? Is it something that everybody kind of knows already, or is climate more mysterious?
I think I probably learned all of that when I was in school, but then it becomes less a science fact and more just experience in living. And so the details I've lost. So all of that was a great reminder of the things I learned when I was younger, and an understanding of why the things I observe happen. So I enjoyed it a lot, because it just helps to give me a basis for what I'm observing again. And it's interesting to know those kinds of things, so that when somebody asked a question about hurricanes, so when weather patterns occur, you can think, oh, I understand that. Or, why does Siberia look like whatever? It just helps you understand those kinds of things. So I enjoyed it. I like that as a foundation.
Cool.
And I liked that you included the Porcupine Mountains. Thank you.
Yeah,
In
I
Michigan.
thought you would get a kick out of that. You
did.
probably recognize that place. It's right by Lake of the Clouds.
Right, exactly.
Yeah. Wonderful place. For those of you who have never been there, you should definitely go there. It's absolutely stunning.
It is. I've hiked there before too. Well, you can see from the picture. Oof.
Yeah. Yeah, it's perplexing to me that because the real basics of climate are pretty simple, why there should be so much misinformation and so much skepticism about the consequences of changing atmospheric composition the way we have seen. Because it really, a bunch of that stuff is kind of from first principles, should be pretty obvious.
Don't you think we're kind of forgetting the gas laws? We're kind of forgetting some of that stuff. And I think, Stefan, you've made the point in the past that, yes, you might be able to go back and say, yes, there have been hot periods, or yes, these things have happened, and sure, it's cyclical, but you have to look a little longer than a decade, or a century, or in the long run, there are big changes. And we so often tend to just think about what's affecting us today, or maybe we'll go back to our grandparents, or maybe when I was a kid and there was a lot more snow in Detroit than there is today. Maybe we'll do that, but not, kind of not in a longer period.
Yeah. Yeah, here's an interesting thing. Let me just share this. Can you see this figure?
Yes.
This is really fascinating to me, because people will point out, I mean, yes, the Earth has been warmer in the past than it is now, but that's the entire existence of agriculture on a timeline. Okay. So everything that we know about feeding ourselves and feeding large numbers of people only goes back about 10,000 years or so. And that's what the temperature has been like over the period during which we've had agriculture. It was a lot colder before that, obviously. It was, an ice age before that. But our human experience of how to live in the world in the way that we do now and feed large numbers of people has been during this really, really stable temperature period. And now it's going up. We're getting out of that, that portion of it that we're familiar with pretty rapidly.
Dr. Murray, I think we also forget that probably the majority of people are not well educated and do not understand or are familiar with what you have presented today.
Well, that may be. I mean, that's kind of why I asked the question. I think that I remember. Of course, this is a very long time ago now, but remember, learning about the influence of the tilt of the rotational axis and the consequences of that for producing the seasons. But I think one thing that I wasn't taught very much, at least as an undergraduate or a high school student, was about absorbance spectra of different gases. And that's kind of where the influence of increasing the carbon dioxide concentration and methane concentration and nitrous oxide, that I would not have gotten except in absorbance spectra of different gases, yes, but not in the context of the ones that we're changing. I wouldn't have gotten that before I took chemistry courses in college, I think.
Mm-hmm.
But it's, like I said, we don't have to have satellites to measure those things. You measure those things in really gory detail in the laboratory. And they've been well understood now for decades and decades and decades. So maybe it's something that we need to, I am of the opinion, just as an educator myself and just a citizen of the weird times we live in, that we probably need to reorient a fair bit of our educational efforts toward recognizing controversies, recognizing, teasing apart the assumptions that go into different kinds of competing truth claims, and understanding how to go and get reliable information in order to differentiate between competing truth claims. I think all of that is sort of part and parcel of what a lot of people call critical thinking, but when somebody just says critical thinking, they're not really telling you what comprises critical thinking. But to me, those are the things that we really need to spend more time on. Even at the expense of understanding the gas laws. I mean, if you have a reason to go and learn the gas laws, you can go and do that. But more of our general education needs to be about separating baloney from reality.
Yes.
Dr.
Definitely.
Spence.
What's that?
Dr. Spence, go ahead. You've had your hand up for a while.
Yeah, I've got a question on Mauna Loa Observatory in Hawaii. We have this very detailed CO2 concentration in the atmosphere. But is there anything similar for methane? You said that methane is critical, and we've got more of it coming out now than we used to. Is there a similar graph of methane concentration as we have for CO2?
I'm not sure how many sources of that there are. I mean, there are lots of sources of information on methane concentration. That graph that I showed actually has a couple of them listed. There are a couple of different data sets on that same graph, but I think those also have to be measured at different altitudes. The the residence time of methane and therefore its effect as a greenhouse gas depends on what elevate, what altitude it's at. And so I don't know whether those are, measured, in some cases with balloons or or with aircraft, but I don't think there's a particular one location where you have methane measured. After all, the reason why they started doing that on Mauna Loa was that it's far away. It's out in the middle of the ocean. It's a tiny landmass in the middle of the ocean, and it's far away from most industry. That's why they have used that data set so much. I think in the last couple of years, they've actually shifted that to Mauna Kea, because when Mauna Loa is erupting, when there are eruptions close to there, it changes the CO2 concentration that's measured. So eventually they'll shift it back there. But I think since the last couple of years, when they've had so much eruption close to where the measuring observatory is, they've actually moved it to one of the other sites there. But my guess is the same thing is true of methane. That's probably really spotty, and there must be certain locations on the Earth that you would get a reliable measurement that's independent of those local effects. But I admit I don't know.
Thank you.
I think a good place to look for these kinds of gas concentration data is the NOAA website, NOAA. If you put in NOAA CO2, you get all the graphs from Mauna Loa and so forth. And they do have graphs for methane there as well.
Okay.
NOAA CH4. I don't know what algorithm they use in terms of measurements at different altitudes, but I imagine they must be doing something like that.
Yes, I think that with the permafrost melting, I mean, I've read increases of methane in those areas, but I really can't recall where they got their data from. So there must be a study going on with permafrost.
Yeah. You can measure that on a really local scale. I mean, essentially at ground level, and then you can interpret. You can measure the amount of methane that's coming out of the ground, and then you can, extrapolate over a larger area. So, all of those measurements are there. I mean, they're all valid, but it would be really nice if we knew that there was a repeatable, reliable measurement that kind of measures the average worldwide. But, local effects are definitely important. And, there's methane hydrates, at low temperature in the oceans too. And as the oceans heat up, more methane is likely to be released there as well. But that's a great example of a positive another positive feedback. So the Earth, and in fact, that's one of the criticisms of the Keeling curve, the J-shaped increase, because if you look at that closely enough, it's not completely clear whether the increase in carbon dioxide precedes the concentration of, or the temperature of the Earth, or whether it's the other way around. And of course, it's both. Because as you increase the temperature, you also increase the release of carbon dioxide. And the same is going to be true with methane.
Well, I like what you were saying earlier, Jill, about how we need this as part of our fundamental understanding, because people don't often think about, okay, we change the Earth's average temperature. How does that affect species? And, I think they can if you tell them, yeah, okay, they're going to be moving northward. But if they know about the life zones, if they know about where these different biomes are, it's easier to envision, oh yeah, all of this stuff is getting shifted. If you don't know that, then you kind of have to take a few steps when somebody tries to explain it to you.
Yeah. One of the interesting things about that too is that you know, the distribution of plant communities in North America, we have a very rich history of that. As the glaciers advanced and retreated, the distributions of plant communities migrated north and south. And in fact, we're still, species are still moving north as a result of you know, from the end of the last ice age, which was tens of thousands of years ago, or about 10,000 or 10 or 15,000 years ago. That recovery and movement north is still taking place, but all of that has to happen through seed dispersal and stuff like that. And of course, once we have modified the landscape so much through changing land use patterns, there may not be corridors, you know, that remain that are hospitable to those plants and animals to move. And so I've had some discussions with geologist friends that point that out to me and say, well, you know, this has happened before. They'll just move north or south to stay in the right climatic zone. But it's like, we don't really live in that world anymore.
Yeah, I think some of those pollen data up and down the east coast of the United States show that some of the tree species didn't really recover their original range before the Ice Age until over 2,000 years.
Yes.
It took them a long time to get back. But now, of course, all of that is being overwhelmed by the rapid movement of species now. All species that can are moving northward and up mountainsides.
Yeah. Yeah, and that's fascinating too. I mean, there was a paper in Science just, well, I don't know, it's probably 6 or 7 years ago now, but a group went back to Alexander von Humboldt's data from Andean volcanoes, in which he during the 1800s, he mapped out in really great detail the distribution of plant communities up the side of the volcano. I think it was Chimborazo in Ecuador. And they went back and recensused along the same places that he did and found that there had been an upslope movement on average, like 400 or 500 meters elevation over that period of time. And I have even observed that myself because I work in tropical mountains, and I mean, Stefan said during in introducing me that Monteverde was one of the first places where the biological consequences of climate change were documented. And that's true. The extinction of the golden toad, which is a really famous endemic that only occurred in that area, it's gone now. It's globally extinct, but the same papers that documented a lot of that documented the upslope movement of a whole bunch of bird species and reptile and amphibian species. And of course, once you get to the top, there's no place else to go to stay in. And so I've been working in the same place since 1980. And I can tell you that there used to be places along the trail system where I would stop seeing this species of redstart, and I would start to see the higher elevation replacement of it. That has moved way up, and I hardly ever see the high elevation one anymore. It used to be that I would never see things like keel-billed toucans near my house, and my house is almost exactly at about 1,450 meters elevation. Now I see them at my house all the time. There's been a really strong upslope movement of a bunch of those things, and of course a decrease or extirpation of the ones that were already at the tops of those mountains. And in fact, that was actually predicted by some climate modelers, that tropical mountains would be the first place where you would find these changes, because the cloud bank, which has a really strong influence because these are cloud forests, the cloud bank would move up higher than the top of the mountain, and it would get much drier, and it would have a profound effect on the animals and plants that live there. And it was at a conference that some climate modelers who were who were detailing that, presented that. And Alan Pounds, a good friend of mine who works on amphibians and reptiles there in Monteverde, said to them, he raised his hand from the back of the room and said, "I have data that show exactly that thing." So lots of parallel, sets of data that all sort of lead in the same direction.
And we're seeing that a lot in Arizona too. So there are studies on how all the grass species in the southern Arizona mountains have moved uphill. Projections from the 1990s about ponderosa pine being here around Flagstaff, being outside of its range of growing conditions when about the time we reach 2 times CO2. And so if background was 280, 2 times is 560, we will reach 560 sometime this decade.
Yeah, we're getting there.
And we're already seeing ponderosa pine it's not recruiting saplings at the lower elevations of its current range here. That's what the forestry professors tell me. And you can climb a ridge out here and look across the forest, and it's just full of brown spots, not just along the roads, out in the middle of the forest. So it's already dying.
Mm-hmm. Yep, it's perplexing. Well, anyway, if there aren't any other, go ahead.
I was just going to say, and we see animals like javelinas and coatimundi noticeably moving up northward into Flagstaff area.
Are you seeing coatis up in Flagstaff?
We are, yes.
That's fascinating.
Yeah, they never naturally co-occurred with ponderosa pine trees, but my neighbor took a picture of a beautiful coati halfway up a ponderosa trunk where the neighbor dogs had chased it.
Huh.
But they're not native to here at all.
Yeah, that's astounding. I mean, both the things that we call javelina here are collared peccaries, of course, and it's a tropical rainforest animal that reaches the northern part of its range in the arid southwest, but it's moving north. And the idea that coatis, which I'm really familiar with from my field site in Costa Rica too, the fact that they would be as far north as Flagstaff is mind-boggling.
So I'll send you the picture of a coati, and you can use it in
that's cool.
presentations.
Anything else?
Well, one thing while we're talking,
go ahead.
The fossil record also shows for small mammals that prior to the last ice age, all these small mammals were distributed in a certain way, and you found co-occurrence of certain species in certain locations. The ice age came through, they all moved further south, then the ice receded, and they didn't necessarily go back to the same places they started at. So you got reshuffling of ecological communities even then when the climate change was happening at a much lower rate. Now we're seeing complete rearrangement of things.
Right. We're seeing the creation of biological communities that have not existed before. And actually, this is something else that's really interesting, and it's sort of counterintuitive too. And I think this is one of those things that very few people know, because when you watch the television and they show where the most where the greatest amount of temperature change is going to be, it's at high latitude. Okay, so the closer you go to the North Pole or the South Pole, the greater is going to be, and already is, the temperature increase. And that would lead you to believe, and of course we all worry about polar bears and stuff like that. That would lead you to believe that the threat to biological communities was highest at high latitudes too. Exactly the opposite is actually the case. And the reason has to do, it actually goes back to kind of a classic paper that Dan Jansen wrote and other people wrote about before he did. And he wrote a paper once called "Why Are Mountains Higher in the Tropics?" And of course, they're not really higher in the tropics, but because organisms that occur close to the equator, that is in the tropics, don't have to deal with as much seasonal variation. In other words, they don't have to be able to live through the winter. They can be more narrowly adapted physiologically to the conditions at the elevation where they happen to occur. And one of the reasons, I mean, that's one of the things that drives the high biological diversity of the tropics in comparison to the temperate zone. There's a sort of a smaller geographical range of tropical organisms, and they're more, more tightly adapted to the conditions where they occur. And so when even a small climatic change has a greater effect on organisms in the tropics. And so where you look at, like the bioclimatic envelope modeling and stuff like that, where we're expecting the greatest losses of biological diversity is in tropical mountains. So it's like in the Andes in particular, because the Andes have so much topographical diversity and so many species that have relatively small geographic ranges. That's where the majority of the loss of biological diversity is going to be, even though the temperature change is going to be less than in the Arctic or Antarctic. And that's kind of counterintuitive, I think, but really important because, of course, the tropics are where most of the biological diversity is.
Yeah, some parts in higher latitudes have already seen as much as 3-degree temperature rise, and already, to put it in human perspective, corn production in Iowa, the king of corn, right, is now volatile, whereas corn production in northern Alberta is rising steadily.
It's going to make the Canadians happy for a while.
Yeah, it's not just for our kids. We're in the full crisis mode now.
Yep. Well, thank you all for showing up.
Thank you for presenting. I like this series. I'm going to sign up as I'm able all along the way. It's a great idea.
Yes, I agree.
Thank you so much. That was fascinating.
Thank you.
And very educational.
Thanks. Well, that's always a good thing too. Should I stop recording here, Stefan?
Yeah, sure. That sounds
Okay.
Okay.